will discuss Ehrenfest theorem. It brings out the fact that the expectation values of quantum mechanical observables follow classical equations of motion. The expectation values of displacement and momentum obey time evaluation equations which are analogous to those of classical mechanics. We are going to derive these two expectation values separately in this session. The theorem is similar to Newton's second law of motion, but it applies to the average or expectation value of a particle's position or momentum rather than the particle itself. Yes, the laws of classical mechanics hold good for expectation values. It bridges the gap between classical and quantum mechanics. That is, the theorem shows that quantum mechanics correspond to classical mechanics in certain circumstances. It is named after Austrian theoretical physicist Paul Ehrenfest. Bohr's correspondence principle, which states in the limit of large quantum numbers, the relations of quantum mechanics reduces to the relations of classical mechanics. It was first worked out by an Austrian physicist Paul Ehrenfest in the year 1927. Ehrenfest suggested replace the dynamical variables of classical mechanics with the expectation values of quantum mechanics and you will get the same relations. The principle of correspondence between the motion of wave packet and the motion of classical particle is projected as fundamental significance. The expectation values of the quantum mechanical operators obey the laws of classical physics. It is defined as the expectation values of the displacement and momentum obeying the time evaluation equation to those of classical mechanics are given by the expectation value of the momentum is equal to the product of m and the derivative of expectation value of position and the expectation value of the force, which is equal to the rate of change of momentum, the rate of change of expectation value of the momentum. Equation 1.65 are called Ehrenfest theorems. We are going to derive these two expressions separately in the session. They are quantum equivalent of the equations of motion of a classical particle. In other words, the average motion of a wave packet agrees with the motion of the corresponding classical particle. In the limit when the wave packet associates with the particle reduces to a point, one expects the particle to behave like a classical one. So we can say that the uncertainty principle limits the equivalence between quantum mechanics and classical mechanics. It provides the mathematical support to the correspondence principle and it is closely related to Livolli's theorem of classical mechanics, which involves Poisson bracket. Let us consider one-dimensional motion of a particle of mass m. The time derivative of the expectation value of position is given by equation 1.66. We know that the expectation value of any quantum variable, quantum operator, can be written as the operator sandwiched between the normal wave function and the complex conjugate. So we can write this equation exactly as it is, 1.66. Now we can differentiate with respect to time, and we know that psi is the function of position and time. So we'll have to differentiate this one first, then we'll have to keep this as constant, plus keeping this as constant, we'll have to differentiate this. So equation 1.67 equation 1.67 is obtained. See, we are going to differentiate this. So d psi star by dt, keeping this as constant. So xi plus keeping this as constant, we are going to differentiate this. We will get d psi by dt x psi star dx. We know that time dependent Schrodinger equation is given by this equation. So kinetic energy plus potential energy equal to total energy. Now this equation 1.68 can be written as bringing this I gets cross to the right hand side. We will have d psi by dt which is equal to 1 divided by I gets cross kinetic energy plus potential energy. Now multiply and divide by I, that you will get minus I by h cross minus h bar squared divided by 2m partial d squared psi by dx squared plus d psi. So multiply this minus I by h cross to inside, we will have d psi by dt, which is equal to I h cross, minus and minus and minus will get plus. So I h cross divided by 2m, h cross and h cross, one h cross will get cancelled. We have I h cross divided by 2m, d squared psi by dx squared, then minus I by h cross d psi. Now take the complex conjugate of equation 1.71. We will have equation 1.72. Here, as we discussed earlier, V is an operator. Take the complex conjugate, you will get V dagger. So now we are going to substitute these two expressions, 1.71 and 1.72, in equation 1.67. 1.67 is given us exactly in here. So we are going to substitute 1.72 and 1.71 in this expression. So we will have this. So this is nothing but d psi star by dt, and this is nothing but d psi by dt. So equation 1.73 is obtained. Now we just multiply x, y inside. So we will have first term multiplying x, y inside to the second term, we will have the second term. Similarly, for the second expression in equation 1.73, we will have this term and this term. So we have four terms now, and second term and fourth term will get cancelled because of V is the condition operator. So this four terms can be simplified as 1.75. So like two terms. So this is your first term and this is your second term. And I have written as interchange. See, I have interchanged the term and I have written. So second term goes with first term, and here first term goes with the second term. And x, I can pull x out, and I can pull one derivative out, and this equation can be written as exactly like this. Say I have pulled one x out, and I have pulled one derivative out. So d by dx of psi star d psi by dx minus psi d psi star by dx. Now I can integrate this one by integrating by parts, UDV method. So this part alone. So I'm going to keep this as u, the whole thing as dv, x as u, this whole thing as dv. So the formula goes with udv equals uv minus vdu. So I'll get as u, see here, it is whole thing as dv. So v is nothing but, we'll remove this one. So this is nothing but your v. dv equals the whole thing. So v is nothing but this part alone, you will have v. So you have x psi star d psi by dx minus psi d psi star by dx. So this is your v. So this is u, this is v, minus v du. So this is v, du, u is your x. So d is nothing but your 1. So multiply by what? Dx. And look at this term, when you're going to apply the limits, at x, as x tends to plus or minus infinity, psi becomes 0 and psi star also will become 0. As we know that this is the physical property of any wave function. So this term will become 0. We will have only second term alone with a minus sign. So equation 1.77 becomes exactly like this. So I have written the same equation. So here, so I have written the same equation here. Now we know that the expectation value of the momentum is given by, we know, the P operator sandwiched between normal wave function and its complex conjugate. And we know the expression for P operator is given as minus I h cross d psi by dx. So you pull minus I h cross out, we will have this. And bringing I h cross to left hand side, we will have minus into plus infinity with integration psi star d psi by dx partial d psi by dx, which is equal to minus the expectation value of P divided by I h cross. Take the complex conjugate. So we can take the complex conjugate, we will get this expression. Now we can substitute these two expressions in this equation 1.7 8. So we will have minus IH cross divided by 2m integration with the limit minus the plus infinity partial d by dx minus expectation value of p divided by IH cross minus expectation value of p divided by IH cross. You can pull IH cross out. Then minus 2p we will get minus 2p minus minus plus, so you'll have minus 2IH cross divided by 2m IH cross. These 2IH cross or 2IH cross will cancel, remaining will be your m, and d by dx and this integration will get cancelled. We have expectation value of p. So rate of change of the position, average value of the position, which is equal to the expectation value of momentum over m. So in one dimension, this can be written as the average value of px is nothing but m, the rate of change of position. So this is one of the Ehrenfest theorems. In the limit, the wave packet reduces a point expectation value when x equal to x, the expectation value of px equal to px, we can get the classical equivalent expressions as px which is equal to m dx by dt. Now we shall derive the another Ehrenfest theorem. We know that the rate of change of momentum is equal to the negative gradient of potential. That is, the force is equal to minus del V. We know F equal to dP by dt. So dP by dt which is equal to minus partial dV by dx. We know already this. Now just take the expectation value of equation 1.80. We will have equation 1.81. Now we know that the expectation value of the momentum in one dimension is given by this expression 1.82, that is the operator P sandwiched between normal wave function and its complex conjugate. Now substitute the expression for your momentum operator, we will have this. You pull minus IH cross, we will have minus IH cross minus into plus infinity psi star partial d psi by dx dx. Now apply equation 1.84 in left hand side of equation 1.81. So we are going to differentiate this, that's all. So we are going to differentiate with respect to t. So we'll have d by dt, expression value of momentum which is equal to minus IH cross d by dt psi star d psi by dx partial d psi by dx dx. And of course psi depends on both x and t. So we'll have to differentiate psi star keeping this as constant, and we will have to differentiate d psi by dx keeping this as constant. So differentiating equation 1.85 with respect to time, we will get this 1.86. Now look at the second term. Here in the expression we have second term partial d by dt multiplied by partial d psi by dx. Here x and t are independent variables, so we can exchange that we can rewrite exactly as the equation 1.87. So the second term we have rewritten exactly as partial d by dx multiplied by d psi by dt. Now we know that time dependent Schrodinger equation is given by this expression 1.88, and bring this IH cross to this side, we will have expression 1.89, and multiply divided by I, we will have this equation 1.90. So taking minus I by H cross inside, we will have d psi by dt which is equal to IH cross by 2m d square psi by dx square minus I by H cross v psi. Now take the complex conjugate of equation 1.91, we will have this. Now we can substitute these expressions, equation 1.91 and equation 1.92 in equation 1.87. So we have 1.87 is here. So this is d psi star by dt, this one, and keeping d psi by dx as it is, and this will have d psi by dt keeping partial d by dx as it is. So equation 1.93 is obtained. Now we are going to separate the kinetic energy and potential energy term of equation 1.93. So we are going to separate kinetic energy part and potential energy part out. So first we will pull minus IH cross out. So we will have minus minus plus. So we will have IH cross divided by 2m, and this you will have d square psi star by dx square and with the multiplication of d psi by dx here. And here you have, in the second term also we have kinetic energy part. So we have pulled out. So this will have minus sign. So minus sign minus I star d by dx, partial d by dx, multiplied by d squared psi by dx squared. The whole thing is kinetic energy part. Now taking the potential energy part. So minus I h cross. Here we have I by h cross. So I by h cross. The potential energy of the first term will be v psi star d psi by dx. The potential energy of the second term will be minus I star d partial d v psi by dx. Now this I h cross and I h cross we will have minus h bar square divided by 2m. You keep this term as it is. Now coming to the second part, minus, we have I squared minus 1. So this will become plus, h bar will cancel. We have minus into plus infinity. Keep this term as it is. And we are going to differentiate this term. When you are going to differentiate this term, keeping v as constant, we are going to differentiate psi. Keeping psi as constant, we will have to differentiate v. So we will have second term and third term. So first term let it be as it is, and we are going to differentiate the second term. We will have second term and third term of equation 1.96. And here first term and third term will be cancelled. We have only second term alone. So equation becomes exactly minus I star dv by dx psi dx. See here, exactly like this. Now remaining these things are let it be like this. I have pulled this minus sign inside, minus dv by dx. What is the second term? This term, this is minus dv by dx sandwiched between normal wave function and the complex conjugate. So we can say that the expectation value of minus dv by dx, which is the gradient of potential field. So we can write this expression as minus dv by dx. These expressions let it be like this. Now we are going to solve the first term. Now taking the second term of kinetic energy part in equation 1.99 and integrating by parts, we have just take the second term. See here we have the second term here, and we are going to integrate this one by parts. So psi star partial d by dx, d square psi by dx square dx. Again udv method. So we are going to consider psi star as u and remaining term as dv. And when you're going to get, you will get only for v, we will get d square psi by dx square. And uv is nothing but, u is nothing but psi star, p is nothing but d square psi by dx square with the limit minus into plus infinity minus, this is your v, so du, so v du. So this is your v, and d is nothing but d psi star by dx. As usual, when x tends to infinity, plus or minus infinity, psi and psi star will become 0. So this will become 0. We will have only this term alone. So the second term of kinetic energy part in equation 1.99 can be replaced by this expression. So we have this, already one minus sign is there. So this minus sign will have plus sign. See here we have plus sign. So the expression 1 and 2 is as shown in equation 1.101. Now this expression, in the first term, we can pull partial d by dx out. So d by dx, d psi star by dx, d psi by dx. We can write exactly the first two terms like this. See, you just differentiate with respect to x. We'll have this term. See here. When you're going to differentiate this, keeping this as constant, you'll have to differentiate this. Plus, keeping this as constant, you'll have to differentiate it. You will get this expression. For example, you just differentiate. You will get d squared psi star by dx, the first term. Keeping this as constant, d psi by dx. Now we are going to differentiate this. We will have partial d squared psi by dx squared. Keeping this as constant, d psi star by dx. So these two terms can be written exactly like this. That can be replaced in equation 1.102. Now d by dx. See, look at here, d by dx. This partial dx and dx will cancel. You have d partial d alone and partial d alone. Integration and the differentiation will get cancelled. You will have this term with the limit minus into plus infinity. As usual, when x tends to infinity, your d psi by dx will become 0. Similarly, d psi star by dx also will become 0. So this term will vanish. The remaining terms will be d by dt, the expression value of the momentum, which is equal to minus dv by dx, which is equal to force. So this is another Ehrenfest theorem. Thus, the expression value of the rate of change of momentum equals to the expectation value of the force given as a negative gradient of the potential. This equation is exactly equivalent to the equation of classical mechanics, with the expectation value of the momentum playing the role of momentum of the particle. This is similar to Newton's second law of motion, which has been derived from short in the time dependent wave equation. Hence, we can conclude that the quantum mechanics corresponds to classical mechanics in the limit that the spatial extent of the wave function, which is typically of the order of de Broglie wavelength, is negligible. This is an important result because we know that classical mechanics is the correct answer in this limit. Thus, the wave packet moves like a classical particle, and the expectation values are the real values in classical mechanics. Thus, the rate of change of momentum is equal to the force, which is Newton's second law of motion. It states that Schrödinger wave equation leads to classical, which is nothing but Newton's laws of motion on the average. For large quantum number, the classical and quantum mechanics give the same result. So to conclude, this reduction of quantum mechanical dynamics to the classical trajectory is known as Ehrenfest theorem. Suppose if I h cross del instead of minus I h cross del is used as the operator for P, we know that P operator is given as minus I h cross del. Suppose if you are going to use instead of minus I h cross del, P operator as plus I h cross del, we will get exactly equation like this. See here, like this with a minus sign, which is not quantum analog of Newton's second law of motion. Thus, the selection of the operator minus I h cross del for the dynamical variable P is just justified.